Hello, in this video we are going to look at the concept of index notation and try to apply it in the context of tensor calculus. So first of all, we need to define a coordinate system. And I'm going to define three axes, so I'm going to work in 3D, but that can also be applied to any dimensions. So I'm going to have E1 here, the direction E2 and E3, in such a way that these E1, E2 and E3 are the axes of a direct orthonormal system. And based on this coordinate system, I'm going to give you a few examples. So let's just move directly onto examples of tensor quantities. So first of all, we can look at a vector, the vector velocity, for instance, which is u, and I'm going to write u as u1, u2, and u3, corresponding, for instance, to the velocity u1 in the direction e1 plus u2 in the direction e2 plus u3 in the direction e3. And you can notice that when we write this, well, the fact that we have taken e1, e2, and e3 in such a way, then we can essentially combine this writing into a much more compact form, which is a sum from e equals 1 to 3 of ui times the vector ei. Okay, and then we can extract from this components of these vector, and these components in general form are going to be written as ui. Okay, so this is a key observation that we can make here in the context of vector calculus. Another quantity that we can look at would be, for instance, in the context of fluid dynamics, the gradient of pressure. And so the gradient of pressure will take the form dP by dx1, sorry, dP by dx2, and then dP by dx3, where x1, x2, and x3 are the coordinates in the e1, e2, and e3 directions. That can also be written as dP over dx1 e1 plus dP over dx2 e2 plus dP over dx3 e3. And while using the same sort of notation, we can write that this is the sum for I equals 1 to 3 of dP over dxi times the vector ei. And therefore we can say that this vector has components dP over dxi. Okay, so this is a second example. And then to conclude these examples, I'm going to take the example of a matrix. So a tensor of rank 2, and I'm going to take an example, for instance, taken from fluid dynamics, which is the gradient of u. So that would be du1 over dx1. Then on the same line, I'm going to have du1 over dx2, and then du1 over dx3. Again, I'm taking this into in 3 dimensions. On the second line, I'm going to have du2 by dx1, then du2 by dx2, and du2 by dx3. And on the third line, I'm going to have du3 by dx1, du3 by dx2, and du3 by dx3. Okay, and that forms my gradient of velocity matrix. And then from this I can extract, in a similar fashion as I did for the two other quantities, I can extract the components. And these components are going to be dui over dxj. There is a little bit of a convention here, and that convention is that I'm going to use I as the row and j as the column. So these are just conventions. We can swap these conventions, but in the context of this course, we're going to keep that convention this way. So based on these definitions, there is some further interesting work that has been done in the context of this index notation, and which we will be using, and it is the use of the Einstein convention. So this Einstein convention is going to simplify our life quite dramatically, and it's just based on two simple rules. So let's have a look at them. The Einstein convention. So as I said, it's made of two rules, very simple rules. The first of these rules concerns what's called free indices. What a free index is just a suffix that appears only once, okay? For instance, here, I and j are free indices. So the number of free indices that a quantity is constituted of indicates its type. So for instance, if we have 0 free indices, we are dealing with a scalar. If we have 1 free index, we are dealing with a vector, and so on and so forth. And so if we have n free indices, we're going to be dealing with an n-rank tensor. Okay? So this is essentially what these free indices are. And so when we add or equate term, they have to have the exact same free indices. So terms, that's the rules. Terms that are added or equated have to have the same free indices. So it's not only the same number of free indices, but also the exact same free indices. Okay? So that's the first rule. It deals with these free indices. The second rule concerns what we call dummy indices. And the dummy indices are just suffixes that appears twice. Okay? The rule with these indices is that we sum over these indices. So this is the second rule in the Einstein convention, is the summation over dummy indices. And there's an extra rule that can help us, in a sense, make a better, a more nicely formed object, which is that we can change the name of a free index provided that we do not use a letter in use for a free index. And this is going to essentially allow us to form nice expressions and to manipulate this expression to do efficient vector calculus. So provided these rules and the Einstein convention, that we can proceed to some vector or tensor calculus. But before doing so, I'd like to introduce some special tensors. And these special tensors, I'm going to introduce two of them. So the first of these tensor is the Kronecker delta. Okay, so this is a second rank tensor. So I'm going to put 2 bars on top of it so that we can keep track of its dimension. And its definition is very simple. So delta ij, 2 free indices, so that's a second rank tensor, is 1 if I equals j and it's 0 otherwise. Okay, and in such a way that this Kronecker delta corresponds to the components of the identity matrix. Okay? So if I try to give you an example on this, of its use, I can, for instance, write down an expression with a vector ai here, and another vector bj, and I'm just writing completely different indices so that they are not related at this point. And if I put a Kronecker delta with the indices I and j here, what I am doing is saying that this expression is always 0 unless I equals j, in which case the Kronecker delta equals 1. And so that leaves us with this following expression ai bi, which is the same as ij, as aj bj, of course. This is nothing else than the dot product between the vectors a and b. Okay, so this is one interesting use of this Kronecker delta. When we are doing this, some people in the jargon, and I'm using this in particular, used to say that we'll contract the indices. So in other words, we'll make one index into the other. Then that's something that is given to us by this Kronecker delta. So this is ai bi or aj bj, as I was mentioning, which emphasizes the fact that these are dummy indices. We sum over these indices, and therefore we can change the letter that we use for these indices, provided that we don't use a letter that's in use for a free index. And this is what we can do here. We can also write ak bk, for instance. That will be the sum a1 b1 plus a2 b2 plus a3 b3. In other words, as I mentioned, the dot product between these two vectors. The other interesting special tensor that I would like to introduce is the alternating tensor. And the alternating tensor is a third rank tensor. So I'm writing 3 bars, but in general I'll just keep myself with 2 bars. What this is just defined as epsilon ijk equals 1 if I, j, k are even, minus 1 if I, j, k odd, and 0 otherwise. Okay, so what even and odd means in this context is in terms of permutation. So if I have an arrangement for which I can return to the order ijk, or 1, 2, 3 for instance, using an even number of permutation, then this arrangement is called even. If I require an odd number of permutation between these elements, then it's an odd permutation. And 0 otherwise, what that means is the cases in which I equals j, or j equals k, or k equals I. Okay? So this is what this tensor essentially means. So it's pretty complicated to represent this tensor because it's a third rank tensor, sorry. So it would be effectively a cube, 3 by 3 by 3. Which you can try and look at slices of this cube. I will not do this in this video, but rather I'll show you an example. So for instance, if I write the quantity epsilon I, j, k, aj, bk, first of all, we want to think for a second about what this quantity means. So I've got a dummy index j, k is also a dummy index, but I is a free index. So what this is, in fact, is a quantity with only one free index. In other words, this is a vector, and I'm going to call this vector ci, I being the free index that is on the right side of my equal sign. Okay, so this is a vector that we're getting. Okay, and this is complicated expression is particularly due to the alternating tensor. So maybe it's easier for us to look at individual terms. So if we look at C1, for instance, so I is 1, which means that j and k cannot be 1, right? Because otherwise the alternating tensor would be 0. So I'm left with either 1, 2, 2, 1, 2, 3, 1, 3, 3, or 1, 3, 2. I cannot have 2, 2, or 3, 3 here for the same reason, because then otherwise I would be in that case. So I've got two possibilities. It's epsilon 1, 2, 3 and epsilon 1, 3, 2. If it's 1, 2, 3, then I've got that even, it takes 0 permutation to go to 1, 2, 3. So epsilon ijk is 1. So it's epsilon 1, 2, 3, A2, B3. And the second possible case is epsilon 1, 3, 2, A3, B2. In this case, I require one permutation to return to the 1, 2, 3 order. So this is an odd arrangement of these three numbers, which means that epsilon 1, 3, 2 is equal to -1, and in other words, C1 is A2, B3 minus A3, B2. Okay? We can continue and look at C2, and C2 for the same reason is going to be epsilon 2, 3, 1, A3, B1 plus epsilon 2, 1, 3, A1, B3. Epsilon 2, 3, 1 requires an even number of permutation, 1 with 2, which is the first permutation, and leads to 1, 3, 2, and then 2 is 3 to have 1, 2, 3. So that's 2 permutations. So this is even, and so that will be epsilon 2, 3, 1 will be plus 1. So that's A3, B1. And epsilon 2, 1, 3 requires only one permutation, which is 2 with 1, so that we get back to 1, 2, 3. In other words, it's an odd permutation, and we get minus A1, B3 here. And we can do the same thing with C3. That'll be epsilon 3, 1, 2, A1, B2 plus epsilon 3, 2, 1, A2, B1. This being, again, an even permutation, 3 with 2, so that we have 2, 1, 3, and 1 with 2, so that we have 1, 2, 3. So that's A1, B2. And this is an odd permutation. We need to only swap 1 and 3 so that we get back to the order 1, 2, 3. So that's going to be a minus sign here, A2, B1. And what we recognize here with these three terms, C1, C2, C3, in the arrangement of the components of the vectors A and B, is that it's in fact a cross product. So what we have calculated here, Ci, is epsilon ijk aj bk. This quantity is the cross product between A and B. And it's a cross product for which we've taken the ith component. Okay? Or in other words, C equals A cross B. And you have to be careful that when you write vectors, you have to write vectors on the right-hand side. And here I wrote the component, the ith component here of this vector, so I need to write down the ith component of this vector on the right-hand side. Okay, so with these special tensors in mind, we can proceed to do some tensor calculus or vector calculus. The first product that we're going to look at is the dot product, which we sort of already seen. So dot product. So for instance, if I've got two vectors, two quantities, I'm going to take u and, just for the sake of the example, grad p. Then this, the result is going to be the dot product between two vectors is a scalar. So this is going to be u1 dp by dx1 plus u2 dp by dx2 plus u3 dp by dx3. In other words, you can rewrite this using the sum I equals 1 to 3 of ui dp by dxi, or very simply using Einstein convention, you can just write that it is ui dp by dxi. Okay? Another way of writing this is you could have started using Einstein convention, the Einstein convention. You could have written that u dot grad p was just writing your vector using different indices, the xj for instance, And then because it's a dot product, we can write a Kronecker delta between the two indices. And then these indices will contract and give us ui dp by dxi. And you can note here that we have only one index, that is here. This index is repeated once, or it's present twice, and therefore it's a dummy index, so we sum over this index. Then therefore, this quantity has no free index, and it is therefore a scalar. Another example of the dot product is the dot product that we have between the nabla operator and the velocity u. So when we write this, we can just very simply, using our Einstein convention, write down the nabla operator first. So that's going to be d by dxi. And then we can write down our velocity, that's going to be uj. And then we can just write down our Kronecker delta, because we're here applying a dot product between these two vectors. So we're going to apply the Kronecker delta onto the two indices that we have written up there to form this expression. And as we've seen, when we write down this expression, these indices will contract, and so we can rename this j into an I, giving us the final expression dui over dxi. Okay, so that is essentially our divergence operator. So there's another product that we often encounter in tensor calculus, which is the cross product. So let's have a look at this here. So we've already seen it. For instance, if we have the cross product between two vectors a and b, and the result is a vector, so I have to take the ith component of this vector. We've seen that this was the alternating tensor epsilon ijk aj bk. This is actually quite easy to remember. Epsilon, we always introduce the alternating tensor first, and then write ijk, for instance. I is kept as the free index. You can see that I've written I on the left-hand side. And then j, the second index of the alternating tensor, goes as an index of the first vector, whose cross product we're taking with the second vector. And the last index of the alternating tensor goes as the index of the second vector. So that's one example. And of course, we can just make up other examples, such as the cross product between nabla and, for instance, the velocity. So that will be in the same vein, so epsilon ijk. I'm going to write my nabla operator first, so d by dx with a second index, j, and the velocity uk. Okay? And I'll give us the cross product. So of course, these rules that we've introduced, these conventions that we've introduced, we can extend them to higher rank tensor calculus. For instance, there are other conventions that come into play, but I can just give you some example here of operations that can be useful in the context of fluid dynamics, for instance. For instance, I can take the dot product between a vector and a matrix. So I'm going to write my vector with an arrow and my matrix with double bars here, so that we see that this is a second rank tensor. This is going to be AI. I'm just going to write it in the usual way when I write things in index notation. I'm going to just write down all my indices independently, and then, so I, then j, then k. And then I'm going to focus about the operation that I'm using here. And this operation is a dot product, so I'm going to use the Kronecker delta. And the rule, or the convention here, is that when we apply a dot product in higher ranked tensor, it's going to contract the indices that are next to each other. In this case, it's going to act on I and j, not I and k. So that's going to be delta ij. Okay? And so for instance, I can change, due to this summation, due to this Kronecker delta, I can change this I into this j, or this j into this I. So for instance, I can write that this is AI, capital A, I, K. And given this expression, now we know what this quantity is. This quantity is a vector, because this is a dummy index, it's repeated. this is a free index, it's only present once, and so because there's only one free index, this quantity is a vector. And the component of the vector that we've taken is the kth component. So I have to write sub k here. Another product that I can be looking at, which would be interesting, is to take this matrix dot product with the same vector. So we're just looking at the same product but the other way around to see if it commutes. And when I write this, I'm just going to write it in a similar fashion. So that's capital Aij, lowercase a k. And as I said earlier, these are the two neighboring indices that are going to be concerned by the dot product. So that's going to be a dot product or Kronecker delta between j and k. All right. And so if I write this, I can contract my indices and write that this is ik ak. Or in other words, that is a capital A, I, K. All right? And so when I've written this, having written this, now I know that this quantity now is a vector and I've taken the ith component. Okay? And what you can see here is that these two quantities are not necessarily equal. Right? So if I want to take for instance, the ith component of this quantity, then I have to move this dummy index into a k, for instance. And this becomes an I, okay? So that becomes ak, capital A, k, I. So my free index is still my free index, and I'm taking the ith here component. And you can see that these are not equal unless aik equals aki. In other words, unless the transpose of A is equal to A. So this is one interesting calculation that we can do in tensor calculus. Other interesting calculations that we can look at is the dot product between two matrices, for instance A and B, like this. The calculation is very simple. We just write down first the matrix with its indices, then the second matrix, unrolling the alphabet here. And then there's a dot product that's going to act between the two neighboring indices. So I'm writing down delta, my Kronecker delta, jk, which eventually gives me, contracting the j and the k, I've got a, I, j, b, j, l. Oops, l. L as a subscript. And so having written this expression, what I can see is that j here is a dummy index. So it doesn't count in the dimension of the object that we're looking for. We have two free indices, I and L. So these are free indices. There are two of them. Therefore, we have here a matrix. And we've looked at the IL component of this matrix. And we can go on with that. We can introduce the double dot products between two matrices. There are several conventions for the double dot product here. This is only one of these conventions. So the double dot product, essentially we're writing down our matrix as usual, Aij, B, K, L. So the first dot is the usual dot product, so it's J, K, okay? But that's going to make this index a dummy index, which does not count anymore in the dimension of our object, and therefore these are the two free indices that are going to be contracted by the second dot. So that's going to be IL. So if we unfold this, the first dot or the first Kronecker is going to contract the j and the k, so that gives us A, I, J, B, J, L. And I've still got a Kronecker delta on I and L. And the second one is going to contract I and L. Note here that we cannot contract j with anything because it's a dummy index. And so this is really the only possibility for this Kronecker delta is to be between I and L. And so that gives us A, I, J, B, J, I. And what you can see here is that this quantity has two dummy indices, I and j, and no free index, that means that this is actually a scalar, and I'm actually looking at the scalar quantity here, so there's no need for an index under it. Okay? And the very last thing in this sort of tensor calculus short course that I would like to introduce is the product rule. This is something that we generally see in vector calculus in a very complicated demonstration, and it's essentially A cross B cross C. A way to simplify this expression and say that it's actually B A dot C minus C A dot B. And this is extremely difficult to remember. And this is in general the case with most vector calculus formulae. However, they're extremely easy to use in the context of index notation. And in particular, to remember this formula, it's actually easier to remember it in index notation. And the formula in index notation reads this way. Epsilon I j k, you see that's going to be our first cross product. And then we're going to have a second cross product, which will be epsilon I L m. So notice here that the first index of these alternating tensors is I. It's the same. The other indices are different. Okay? And so this product of alternating tensor is going to be equal to products of Kronecker deltas in the following fashion. So we're going to have delta JL, delta KM, and this is very easy to remember once we've written this down, because this is delta, the second index with the second index, JL, and the third index with the third index, K and M, all right, minus delta JM delta KL, minus delta, the second index of this one with the third index of this one, so JM, times delta, the third index of the first alternating tensor, K, with the second index of the second alternating tensor, L. Okay? So that means essentially this product of alternating tensors, with the first index being the same, is going to be equal to a product of delta, Kronecker deltas, in which the first of these products is the second with the second indices, the third with the third indices, and the second one is the crossed product. So J, the second with the third, and then the third with the second here. Okay? So this is potentially the hardest formula to remember in this in vector calculus, and it's made easier by tensor. Alright, so in this video I've introduced index notation. I have talked about the Einstein convention, and we've looked at how to apply these conventions to be efficient in doing vector or tensor calculus. This concludes this video on the index notation.